Hello, everyone, and welcome to today's webinar, NMR in Standardizing Biomarkers for Personalized Medicine. Where do biobanks come in? Presented by Professor Matthias Nauck, MD, and moderated by Dr. Manfred Krall. I am Alexis Krall of LabRoots, and I'll be producing today's event. Today's educational web seminar is brought to you by LabRoots and sponsored by Bruker. Bruker enables scientists to make breakthrough discoveries and develop new applications that improve the quality of human life. Bruker's high-performance scientific instruments and high-value analytical and diagnostic solutions enable scientists to explore life and materials at molecular, cellular, and microscopic levels. For more information, please visit www.bruker.com. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click on the Send button. Your questions will be addressed by the speakers via the contact information you provided at the time of registration. If you have trouble seeing or hearing the presentation, click on the Support tab found at the top right of the presentation window, or report your problem by clicking on the Answer a Question box located on the far left of your screen. Lastly, at the end of the presentation, you will receive a poll survey, which we kindly ask you to complete. Your answers and suggestions will help improve our webinar program and are greatly appreciated. It is now time for our presentation, moderated by Dr. Manfred Krall.
Hello. So thank you, Alexis, for the nice introduction, and thank you everyone for joining us today. Our webinar today is titled NMR in Standardizing Biomarkers for Personalized Medicine. Where do biobanks come in? It is presented by Professor Matthias Nauck, MD. Professor Nauck actually completed his medical studies at the University Hospital in Freiburg in Germany. In 1997, he became specialist for laboratory medicine after obtaining his doctorate in 1992. He received his habilitation in the year 2000, and since 2002, Professor Nauck is director of the Institute of Clinical Chemistry and Laboratory Medicine at the University Medicine in Greifswald. Professor Nauck, you can now begin your presentation.
Yes, Manfred, thank you very much for this kind introduction, and hello to everybody in this audience. I will start with a presentation, Clinical Metabolomics by 1H-NMR Spectroscopy. According to transparency statement, I received honoraria from Boehringer Ingelheim and Becton Dickinson from consulting, and there are a lot of research support and funding from several companies you can read from this slide. In my talk, I will cover the topics metabolomics, pre- and analytical aspects, the epidemiology and biobanking. I will talk about type 2 diabetes mellitus and markers of glucose metabolism. I will talk about the biological age, lipoprotein subfractions, and fatty liver disease. Starting with the topic metabolomics, we learned over the last decades to get information about our genome, about our transcriptome, the proteome, and the metabolome. And we know that these aspects of these omics are influenced in part by age, diet, drugs, lifestyle, and so on. We are especially interested in the metabolome because the metabolome covers a lot of these different aspects, and the metabolome is closely linked to our diseases. So we have the opportunity to look at the metabolome and to get information about subclinical situations, and this will help us to improve the medicine in future. The metabolomics, as defined, is the entirety of small molecules, typically less than 1 kilodalton in a biological sample like blood or urine, but also in tissues or single cells. We apply the metabolomics for biomarker discovery, for pathway discovery, from pharmacometabolomics for translation of biomarkers, and for instance, in newborn screening, but this is not the topic of this talk today. In general, we apply two different techniques to look into our metabolome. On the one hand side, the mass spectrometry, and on the other side, the nuclear magnetic resonance spectroscopy. Of course, these methods have advantages and disadvantages. The mass spectrometry has a very high sensitivity, and we need only a very small sample volume. It's, on the other side, a destructive technique with relatively high costs and an extensive sample preparation. On the other side, the NMR is highly reproducible, a very important aspect I will show you later. We need only minimal sample preparation, and one of the favorites is a non-destructive technique. The sensitivity is lower in comparison to the MS, and in general, we need higher sample volumes. In future, the combination of both methods is a very important tool, and here you see a picture of the metabolic profiler, where we have the combination of MS and NMR using the same sample using an automatic pipetting robot. And here you can see that the NMR and MS spectroscopy are really combined in one analytical step. When we look at the NMR spectroscopy, you see a spectrum like here from a urine sample, and we have a lot of substances we can really define and measure and quantify, and this quantification is possible through the addition of only one standard TSP, and according to the TSP peak we can quantify all of our substances within the spectra. In general, we have two different ways to analyze these data of the NMR spectroscopy. We have the targeted way and the untargeted way. As I already mentioned, the targeted way, we have the absolute concentration of the spectra, and we can quantify metabolites. So for further statistical analysis, this is a more or less established way to use these analytes as in classical clinical chemistry. And on the other side, the untargeted approach. In this approach, we divide the spectra into small regions, which are called buckets, with a fixed width. And then we look at these buckets and look if there are any associations between the buckets and the height of the buckets in view of some associations to clinical aspects. When we are applying biological samples, we learn from our clinical chemistry and laboratory medicine knowledge that pre-analytic plays a very important role, and that we observe in many situations changes of our analytes according to not sufficient or not adequate sample preparation. And therefore, we look carefully at these aspects of the pre-analytical approach. And here do you see in this slide our study design. We collected urine, and this urine was stored at -80 degrees Celsius. It was stored at 10 degrees Celsius and at room temperature for different time periods. And then we looked at the NMR spectra of these different processed urine samples. And as you can see on this slide, we have overall 10 different subjects. And here do you see the color slides of these points, which were measured after different pre-analytical states. And we can state that the pre-analytic aspects are less strong than inter-individual differences. So we can state that the urine from one person to another person has a quite different metabolome, and the changes which we observe during the aging of the samples is relatively low. The freezing of samples at -80 degrees seems to be sufficient, and the majority of metabolites was stable up to 24 hours at 10 degrees Celsius. We observe changes in urine if there is an infection of the bladder, and then there are substances which change the urine metabolome within hours. Coming back to the analytical phase, I show you on this slide the situation that we measured in our clinical chemistry laboratory. Samples with a request for glucose determination, and we determined the glucose in duplicates just when the sample came in. On the x-axis is the first value, and on the y-axis is the second value, and the sample measurements, the time between these measurements are just minutes. So we can say that we immediately measured the duplicates, and here do you see this the results are not identical, but they are really close to each other, so the analytical way itself is quite precise and accurate. When you look at this sample, this slide, here we remeasured samples which were stored in our biobank for a period of 5 years. And it's always the glucose concentration as in the first example. And here do you see that the deviations are a little bit higher compared to the first slide, but taking into account that the time period is now 5 years between these two measurements, the situation is quite good. When we look at this slide, we measured the glucose concentration in samples after a storage period of 15 years. And of course, the scatter is a little bit higher, but in general, we can state that the glucose determination after 15 years gives more or less the same result as in the sample which we measured right on the way when the sample was collected. So in general, we are able to store our samples in an adequate way, especially when we look at the analyte of glucose. In this sample, the vitamin B12 concentration was determined in the original concentration on the x-axis and after 5 years in the y-axis. And here do you see that the younger concentrations are much lower. And of course you can state this is an effect of our pre-analytical phase of the biobanking. But in this situation, the case is a change of the laboratory assay. And this is one of the problems in clinical chemistry today, that changing of assays or assay platforms may have a real impact on the analytics. And when we are looking in epidemiological ways, where we measure samples in the year 2000 and we measure newer samples in the year 2010 or 15, we have real problems if we have changes in of the analytics, because in such situation we cannot state that the vitamin B concentration, for instance, is increasing or decreasing. And therefore the accuracy of measurements is quite important, and this is one of the real benefit of the NMR spectroscopy, because the data are really comparable, independent if their time period between these two determinations is 15 years or more. We started in Greifswald with our epidemiological studies in 1997. Greifswald is located in the northeast part of Germany, and you can see Berlin and Hamburg, and at the Baltic Sea is located Greifswald. And in 1997 we started with a study comparable to the Framingham Heart study. We collected the samples of 4,310 probants and located in this area with an age of 20 to 79 years. And 10 years later we started with another study, SHIP Trend. And these study is very important for our knowledge, which we can detect with the NMR spectroscopy. Overall, we collected in the meantime about 1 million aliquots for our biobank. And the biobanking topic is quite important. And when we look at the literature, we know that in many aspects the biobanking procedures are not as good as they should be. We really need a very high quality process of our sample preparation, the collection of the samples and the storage of our samples. And in many situations it is written that there is an insufficient provision of biomaterial information for publication, stated in Nature in 2011. So it's one of our main aspects to be very careful with our samples and to make the processes sure. And of course we are interested in quality control aspects so that we can state that our samples are okay, which we use for our efforts. In addition to the SHIP study, in Germany we started a few years ago a huge epidemiological study, the so-called German National Cohort. In this cohort we are collecting 200,000 probes all over Germany. You can see the study centers in this landmark. And we collect these samples in 18 study centers, and the major diseases we are looking for is cardiovascular disease, diabetes mellitus, cancer, and so on. On the next slide, you see how many cases we expect during the follow-up period of this study. So we can look at any cancer, and after 5 years, 5,000, 10 years, 13,000, 15 years, 21,000, and 20 years, 29,000 cases with any kind of cancer. This is quite a lot, but when we differentiate our cancers into breast, prostate, colon, lung, and so on, the affected number is quite low, and therefore it's very important to have a so huge cohort that we are able to look at these cases with small numbers of cancer more in detail, and that we will be able to detect, for instance, biomarkers which will be helpful in future to detect these persons as early as possible. The biobanking of the national cohort is mainly located in the Helmholtz-Zentrum near Munich, and we store the samples in a central way in the liquid phase of nitrogen minus 180 degrees Celsius. And here you see a sketch of the biorepository where we have 18 tanks. Each of these tanks has a diameter of 2.5 meters, and these tanks are fully automated so that you can handle the samples even at these low temperatures. We have to be careful when we look at our samples and when we compare our samples from different studies, so that we do not have apples on the one side and pears on the others. And therefore, we are glad that we have now a tool available from Bruker where we can check our biobank samples at the very beginning when we store the samples at the one hand side, and on the other side when we look at these samples over a storage period of 10 years, for instance. And then we have a lot of flags where we have the results available, and one example on the right hand side with the NMR spectroscopy is quite easy to detect if we are using EDTA plasma or serum or heparin plasma, for instance. And in general clinical chemistry, this is quite hard to define. At the end of the way, we have to measure, for instance, potassium, then we can conclude it might be EDTA plasma. But this is a valuable information, and when the collection of the samples we observe some errors, then one of these errors is the exchange of serum or EDTA plasma. Coming to the clinical aspects of the NMR spectroscopy, I will switch to the topic of diabetes mellitus. Diabetes mellitus is, of course, a very prominent disease, and the incidence rates of diabetes mellitus is quite different all over the world. But the main aspects I have to take into account is that roughly 50% of the diabetics currently do not know that they are diabetics. So despite our possibilities to measure glucose, to measure HbA1c and so on, we have really many people which are not aware of this disease in the personalized aspects. And therefore I think we need additional instruments, we need much better instruments to look into the future to detect these people much more early. And I will show you the results of two studies, the SHIP study from Greifswald, here you see where it's located, Berlin and Hamburg, and the Inter-99 study, which is performed with our colleagues in Denmark in Copenhagen. Coming to the study of the SHIP study in Greifswald, there we looked at 2,700 participants, and we had a 5-year follow-up period. In this 5-year follow-up period, we observed 137 new diabetic cases. We looked at the NMR spectroscopy of the urine and performed some analysis. Here do you see the results of this study. On the right-hand side, there are the data of the women. On the left-hand side, the blue fields are from men. And on the x-axis and the y-axis, there are listed the analytes which we determined. And then we calculated ratios between the analytes on the x-axis and the analytes on the y-axis. And when we look into more detail into the data, we have some analytes like alanine, lysine, threonine, and so on. These are clearly associated with diabetes mellitus, and this is a confirmation of previous findings, so it's the established way. On the other hand, we are able to find new analytes which have associations with type 2 diabetes mellitus and the incidence of these cases. And these associations of TMAO and trigonelline are quite beneficial in women. And here you see the ROC curve of our analysis. The yellow line, in this case, we use the urine glucose and the listed analytes trigonelline and TMAO in addition. And then the discrepant is much better, and there's a significant difference between these two ROC curves. So the addition of additional analytes increase the possibility to detect persons with incident diabetes mellitus more in advance. So when we look in changes in the glycemic markers, up to now, mostly case control designs focus on the classification of incident diabetic cases. Gradual changes in the chemic control could be addressed using changes in continuous markers like fasting plasma glucose, glycated hemoglobin, or insulin resistance. And to predict those changes, we are applying urine metabolite measurements. So we want to look into the future applying these urine metabolites, which is quite promising. And within the Inter-99 study, we have two subgroups. On the one hand side, the whole population with nearly 4,000 probants. On the second, the subgroup with no signs of diabetes mellitus, which a number of 1,350 around. And when we look at the data of the urine metabolome measured at the baseline and 5 years later, which are correlated with each other, then we see that there are a lot of analytes which have a quite good correlation between the concentration at the baseline urine and in the urine after 5 years follow-up. And the Spearman correlation greater than 0.4 is a hint of a metabolic fingerprint of these probants. So we see that there is a constant concentration in the urine concentrations, and therefore we can apply these concentrations, these analytes, for medical purposes. And here you see the way how we looked at these data. We observed the percent change in glucose during follow-up by 10% increase in baseline metabolites. So on the y-axis, you see a lot of metabolites, and if these metabolites changed by 10% during this time period of 5 years, we see that the glucose concentration increases by 0.1, 0.2%. It sounds not be very much, but it's obvious for creatinine in collaboration with the glucose, and we have the same finding when we look at the HbA1c or on the HOMA index according to the insulin resistance. So we see changes in our analytes, and we can predict the changes in glucose concentration, and therefore we are able to look into the urine metabolome, and we are able to define people who are at an increased risk to develop diabetes mellitus. When we look at these analytes more in detail, trimethylamine and dimethylamine, these are markers of shifts in the gut microbiome, one of the new omics fields, and this makes absolute sense because diabetes mellitus is closely related to our nutritional habitus. When we look at the changes in the glycemic markers, here do you see the spectra and the different substances in the targeted approach. And in the field below this, we have the bucket, the untargeted approach. And of course, we see that there are areas with a blue sky where we do not find a real analyte, but the untargeted approach gives us the information which is helpful to divide these patients into at risk or not at risk. One of the other aspects we use the urine metabolome is the biological age. And we use the urine metabolome of the SHIP0 cohort as well, and the quantification of 59 analytes. And these analytes are now available applying the Bruker quantification in urine algorithms. And we looked at these data and we calculated the biological age. So of course, we have the chronological age we have presented in our passport. And then we looked at the metabolome and differences in the metabolome. When we look at the skin of a human, it's clear when we have a baby, it has another skin type than an adult or a really old person. And of course, the metabolome has changes with age as well. And we tried to look more into detail, and on the right-hand side you can see that there are situations which makes you younger, like physical activity, and cases which makes you older, like smoking or diabetes mellitus. And we could clearly show that persons with a manifest diabetes mellitus have a higher biological age and therefore a higher risk to develop diseases and to die. When we are looking at the metabolome at all, here we see the age changes from a 20-year-old person to a 40 to a 60 to an 80-year-old person, applying these data from the SHIP study. And we see, of course, there are a little bit changes. In future, we want to combine many data from different epidemiological studies to look at the changes during life, starting in the area of the newborn, and of course in the area when we become older, and then at the end of this age trajectory, these are data from the 20 to 80-year-old men. Currently, we are establishing age-specific reference intervals for the metabolome, and the aim is to develop analytical tools for determination and analysis of these data. And of course, we want to detect people where illnesses are on the way to develop. And of course, we want to look at the metabolome to receive these persons quite early so that they are beneficial in view of additional medical therapeutic approaches. So I want to conclude the type 2 diabetes topic. Subclinical changes in glycemic control have a urinary fingerprint. Those relate to shifts in the gut microbiome, nutritional behavior, and 1-carbon metabolism. And the biological age score is able to summarize complex metabolic interactions. In addition to our epidemiological approach, we established in Greifswald the so-called GANI MED project, the Greifswald approach to individualized medicine. The objective is to use state-of-the-art diagnostics and novel therapeutics interventions that take into account the specific requirements and characteristics of the individual patient in order to optimize the effectiveness of treatments, avoid adverse reactions, and reduce healthcare costs. And we have different clinical cohorts where we perform a very standardized clinical examination, in part a whole body MRI imaging, and of course we are looking at laboratory medicine markers and biomarkers, include the omics approach. And one of the topics for this aspect are the more or less detailed analysis of lipoprotein subfractions. Here you see the lipoprotein composition like a tennis ball, and in the core there are the cholesterol, ester, and triglycerides, and on the surface there are apolipoproteins, phospholipids, the unesterified or free cholesterol. And on the right-hand side, you will see that the size of these lipoproteins is quite different. And we learned over decades that the association, for instance, the LDL cholesterol is the bad cholesterol, the risk of cardiovascular disease development is much higher, and the HDL are protective. On the other hand, when we look more into detail into the class of the LDL, for instance, here's a classical approach with a huge centrifugation, ultracentrifugation process, and then we are able to divide these lipoproteins in further subfractions. On the top, there are the large LDL particles, and down are the small, dense LDL particles. And on the right-hand side, you will see that these subfractions are distributed quite differently. On the left lower hand, it's equally distributed. On the right lower hand, we have only large buoyant and small dense LDL. On the right upper side, we have mainly the mid-size LDL particles, and we know that the risk according to these lipoprotein subfractions is quite different. So very poor are the small dense LDL and in part the large LDL particles, whereas the in-between LDL particles are not so dangerous in the view of the development of cardiovascular disease. So the analysis and preparation of these lipoprotein particles is, with the classical instruments, quite time intensive, and we need about 1 week to prepare these samples. We performed more than 200 such preparations, and in addition we measured these samples with the NMR spectra and applied an algorithm together in collaboration with Bruker BioSpin. And now the procedure needs only 30 minutes. And we measure a lot of substances, as you can see in this overview: triglycerides, cholesterol, free cholesterol, phospholipids, ApoA1, A2, B, and the number of LDL particles. And when you apply these lipoprotein subclass analysis, you receive a lot of results. For instance, the triglyceride distribution over the lipoproteins, and then in addition over the lipoprotein subclasses. The BARC, here you see the distribution of the samples in general, and the concentration found for the actual sample is a black bar. So you can see that in this case the triglycerides concentrations in total VLDL and LDL in general a little bit high, where they are within the confidence considerations in the HDL lipoprotein fraction. And now I will come to the fatty liver disease. Of course, the liver is one of the main organs which is involved in the metabolism of nearly everything. And on the one hand side, we have the healthy liver, and we have the situation that according to overnutrition and insulin resistance, we have changes in the liver, the NFLD, the non-alcoholic fatty liver disease. And if the substances continue, then we have other inflammation stimuli and insulin resistance, and then we'll develop the NASH, the non-alcoholic steatohepatitis. And this is a quite poor position, which is associated with other diseases. And in such situation, in general, we have more cases with type 2 diabetes mellitus, we have more cases with cardiovascular disease, and more cases with chronic kidney disease. So we see that the liver is a very important organ. And when we look in such situations in detail into the lipoprotein subfractions in accordance to the fatty liver disease, and we performed this in studies, patients of our SHIP trend study, where we applied the whole body MRI, and therefore we were able to quantify the liver fat. And then we observed that there is no association between fatty liver disease and the total LDL cholesterol. So a negative result. It doesn't seem to be helpful. When we look more into detail, we see an inverse association with large dense LDL. And on the other hand, we see a real positive association with a small dense LDL. So this is an example from our point of view, which is quite important, that the additional information we receive when we're looking at the lipoprotein subfraction in detail is helpful to classify such patients with such a disease. So I want to summarize my talk. The NMR is a robust, fast, and highly reproducible spectroscopic technique to compile molecular fingerprints through diseases. The highly informative content of NMR spectra allows the development of life trajectories with a single technique. The NMR strongly advances lipoprotein-based diagnostics and risk stratification and its translation to daily clinical practice. And the minimal sample preparation in combination with highly reproducible measurements allow for a worldwide compilation of comparable metabolomics data. So I'm at the end of the talk, and thank you very much for your attention.
Thank you, Professor Nauck, for this very interesting presentation. What I will do now, I will just now give you some additional information on the things that were mentioned here, especially, of course, on the from the hardware side, from the software side, and then also show you some tools which will be important in precision medicine. So let me just switch. So I want to talk about, well, first of all, the platform concept that we are using in NMR, which is helping especially for biobanks, as I hope you will see in a short while, and also show you a few examples for what you can do with personalized metabolic profiles. So when we talk about the IVDr platform, then this is a concept based on NMR, where IVDr stands for in vitro diagnostic research. And what we actually want to achieve with this platform is a completely standardized and fully automated concept based on this platform and the solutions that we are offering into this for clinical and translational research. And of course, it was already mentioned for biobanks, a lot of samples have to be measured, and in several cases, of course, there will be a need to have more than one of such platforms used to actually generate all the data which are stored. You heard about very large sample numbers, 200,000. There are also biobanks which have actually more than 1 million samples stored. So this is definitely a challenge that cannot be executed by a single instrumentation. So that means there is a need to actually integrate data from different user groups, and that could be all over the world. And of course, if you can select such data which are generated, for example, in biobanks, and I will come to that in a moment, or are generated at different groups, like also in the International Phenome Center network, then of course we can be much more efficient in developing also future diagnostic routines. Now you see here a picture of this platform concept. So we start on the bottom with the IVDr platform at 600 megahertz. This is a standard frequency, as it was used a lot in pharmaceutical industry and also in clinical translational research. So this is research use only, and on top of that, actually, we have then the SOPs. We call that our IVDr methods. So these are the standard procedures that we have, for example, for measurement of urine, plasma, serum, CSF, and very soon also further body fluids or extracts thereof. Together with that, there is a spectral compound reference base. We call this B.I.BioBank code, which currently has 800 compounds in there, where we have a lot of 1D and 2D spectra, which are used then to, for example, identify outliers in statistical analysis, and also, of course, play a role in quantification. On top of that, we have then what we call the tools. or enabling tools. So this is the lipoprotein subclass analysis that was already mentioned. There is also a small molecule quantification in plasma and serum. We have then for urine, we have neonate quantification. Also, we have the same for adults and children, and this goes up to 150 metabolites currently and is under constant expansion. Also, we have just introduced now this Biobank QC tool that I will also shortly introduce. If we actually collaborate with other partners or groups, then like in Greifswald, and they are using these SOPs, then of course if they develop certain assays or tools, then this can be actually added to this platform. So it's not only what Bruker BioSpin is offering, it also will be, of course, what our users are able to contribute. Now these SOPs, they act like an internet protocol, for example, because that makes it possible that everybody that is under these SOPs can connect with each other, and of course we can also connect from the Bruker side and do some data analysis, for example. Now I wanted to show you something about reproducibility, which is one of the strongholds of NMR, and this is a result which was done on a ring test with 11 IVDr platforms in 5 organizations in the United Kingdom and Germany. So what we are looking at here is actually just the results of the QC samples which are generated on those instruments, and 11 instruments, as I mentioned, and you can see if we now look into comparability and reproducibility of the data, you see it is exactly on the diagonal, and if we look to the R value, then this is basically 1. So we can also say with this performance, for example, all these 11 instruments, they were able to go into the better than the criteria which are explained or set by the National Cardiovascular Education Program in the US, where you can see, for example, target imprecision, target inaccuracy, and also the total allowed error. This is with this brown bars, and if you look to the greenish one, you can see the results of these 11 instruments, and you see all of them are clearly inside this level. So this is a clear proof for the performance of NMR. Now, as I mentioned, this is very important for biobanks, because what we can do there, of course, we can offer an extensive quality control for incoming samples. That means you can sort out aliquots with very low quality, for example, or at least mark them as having this issue of quality. When we do this QC process, we generate NMR data that can be stored in the biobank together with the metadata, for example. And of course, these data are under complete standardization. So if more than one biobank does this, then all these data, they are comparable. So that means we can actually then also, and you have seen that mentioned, we can add the analysis of, for example, the lipoprotein profiling. We can add the analysis on the urine quantification. All of this can go into the biobank together with the metadata. And of course, then we can also do, if we have the metadata, selected spectra based on metadata that are interesting from this inventory, and later, if this is standardized over multiple biobanks, which is something that, of course, will support clinical trials, which I will explain in a moment. So the workflow, when we look in this biobank tool, so the first thing, of course, are the QC results. So that means when the sample is measured, this QC analysis and reporting is immediately done, and also then immediately available for investigation. And it was already mentioned that we look, for example, in the type of plasma or whether it's serum. We have many more parameters I am going to mention now. And of course, some of them are also NMR related, because NMR will also show us deviations. Now, if we look in, for example, plasma serum or urine, you see it in the upper table. So what is in the orange color, this is for the matrix of urine. And so we can do an identity test again. So is this really urine? We can do an integrity test. We can do contamination tests. And we can look into the preparation on the NMR side and the measurement. We can look into medications. We can look into protein backgrounds. And we can test for further parameters, like, for example, in the urine, whether this was a fasting sample or not. So, of course, medication, for example, is quite important because it is well known that we have a lot of unreported parameters which might not be in the metadata. And of course, here there is a big help to immediately identify whether there is, for example, medication used. And then this would also explain outliers that you might have in any statistical investigation which is done afterwards. So then when we just look to some examples, you see here how we are actually looking into the protein background, because protein background, of course, in urine has different reasons. So like kidney damage, diabetes, high blood pressure, then protein supplement intake, then fever, stress, preeclampsia, and of course that can be compared also to metadata, for example. So you can see on the right side the spectra. It shows a sample which has in black, which has a normal protein background, because there is in most cases always a small background. And you can see the red color. This is now a sample where we have an extensive protein background. Next example here, this is now looking into contamination. For example, on the right side, you see a spectrum in the upper part for plasma serum. And then you can see this yellow indicated peak, which sits on the lipoprotein signals for the CH3. Which would, of course, disturb analysis that would be done. We have taken care of that in NMR, but if you have other tests, then of course it is important to know that there is disinfection material, like in this case, for example. Or we have, for example, cleaning agents in urine, like the isopropanol. On the left side, the spectrum, we can see how we identify, for example, whether this is an EDTA plasma. And I mentioned already that you can add a lot of information besides the spectrum that can go into the biobank. So there would be, for example, the 150 compounds which are quantified automatically in urine. And we have the lipoprotein subclass analysis with up to 115 parameters. And we have the quantification of small molecules, which is done exactly with the same experiment in plasma and serum. So you can add a lot of information to the biobank. Now, let's just think about the clinical trial. So the classic organization you have is to generate these cohorts is you have an organizing group. And of course, this group is working together with other groups that in addition also generate a lot of samples. So that means you really have a large sample cohort. And then, of course, a lot of samples have to be stored, a lot of samples have to be analyzed. So the question is, how could this be done in a different way? So let's assume we have biobanks which are operating according to our NMR SOPs, and therefore, of course, create exchangeable data. Then what we can, of course, now do is, for example, if you look into control data, you could take them also from the NMR spectra, which are stored in the biobank for cohorts, which are, of course, described by the metadata. So that means here could already be a substantial reduction on additional samples that you have to generate for the clinical trial. And like this, of course, you can substantially reduce time and cost. So for at least for this NMR solution based on reproducibility, this is what we can do. Now, I want to go a little bit back into precision medicine. You have already seen this metabolic trajectory, and you see that there are areas where this trajectory actually is quite stable. Of course, this trajectory has been built from a large number of participants. But what you can also do, if you look to an individual participant and you have longitudinal study, then you can, for example, discuss about an index of change in the metabolic profile of this person. And of course, that is shown here on the right side. So if you have a normal development, then the metabolic profile will not really change over several years. And if this starts to deviate, then of course you can change your lifestyle, or you have to take medication at the end. Now, the tool to do that actually, and this was done in a collaboration and a project with Serum in Florence, Professor Lukinat, we have looked into how can we actually reduce this high variability in urine, because of course this depends from what you take in terms of food that you take, drugs, nutraceuticals, how your sports activities are, and this might be different every day. So we have developed a routine here how I can subtract this variability. And you see that here with a person which changes the hairstyle means it's still the same person, it doesn't change. Or another person, we have exactly the same thing. If we now take spectra and we actually reduce the daily variability, then what you can see, if we compare, for example, in this graph here, each of these between the black stripes, these are 40 spectra of one person, and you see in the upper part, this shows the daily variation. If you go to the bottom, you see how this is done after we have subtracted this daily variation. Now I just want to show you how this can be actually applied. And this is now a follow-up study of the initial study that was done, because there we found out that we can identify people by their urinary profile. And if we now look to the change of that, then we have an index of change which could tend towards disease. So you have different people here. Each of the colors is one person. You see here from 2005 to 2015, this study was executed where people have given urine samples, and you see some of them are extremely stable and others have severe deviations. So if we look into that now in more detail, if we start, for example, with the first one, this is this blue colored one in the beginning of the graph. Then this was a female with 2 pregnancies, and in 2014, where this really goes down, the lady was breastfeeding, and the profile changes because now lactose and glycine are up. This is reported for pregnancy and the lactating phase. As soon as the lactating was ended, you can see in 2015 the original metabolic profile actually was re-established. If you look to the red one in the middle, which shows a large change, this was a male which had a longer antibiotic treatment and developed a secondary lactose intolerance in 2014. So that was then the consequence to withdraw fresh dairy from diet. Gut microbiome changes actually could also be seen if you look to trigonelline, hippuric acid, and hydroxyisobutyrate, and some others. Also, this person was exposed to a long-term stress. In 2015, actually the dairy was resumed, no antibiotics anymore. You can see the red curve goes back to the normal profile. And then we have the other dark blue one, which actually goes down, you see, towards the end of this graph. And actually here, this was a lady which also had 2 pregnancies. This was not lactating at collections in 2014, but there was a total thyroid removal because of thyroid cancer. And then a thyroidal hormone treatment started. and which this showed up in a permanent distortion of the metabolic profile. So here it hasn't been re-established. And you see the metabolites which are actually changing during this action. So here you see a very clear tool how you can actually follow up the treatment. Good. Now go back to the slides, and I'm finished in a second. This we have seen. I just want to show one last example, and this is the NMR-based screening using actually treatment optimization in phenylketonuria. So you see here in the different colors, these stars and circles. These are different medications which are taken, and you see the blue cohort, the blue ball represents healthy, and the red one represents then diseased people. And you can see, for example, that the subpropterine dihydrochloride actually can move such a metabolic profile into the healthy version. And of course, you can do that by optimizing the treatment. With that, I'm done. I hope I could show you that NMR supports biobanking by comprehensive quality control, generating additional data that can be used, and also supporting clinical trials. I have shown you that NMR can be used for actually looking into precision medicine and following individual people's actually metabolic profile. So this is good for optimizing the treatment. With that, I would like to thank you for your interest, and so now I have Alexis again with some more comments. Thank you.
Thank you, Professor Nauck and Dr. Sproul, for your informative presentations. If you have a question you'd like to ask, please do so now. Just click on the Answer a Question box just click on the Ask a Question box located on the far left of your screen. We'll answer as many of your questions as we have time for. Also, questions submitted during the on-demand period and those we do not have time for today will be answered by email via the contact information that you provided at the time of registration. If you don't have time to stay with us for the Q&A period, please complete the poll survey before leaving to let us know how we did. Now, let's get started. Dr. Sproul, over to you.
Good, thank you. So start with the questions. The first one, it says here that this is an important presentation and that the slides are needed to further follow up. So Professor Nauck, I ask you to tell us if that is possible. And of course, also this webinar will be on the internet for 1 year. But also just a few remarks from Professor Nauck about that one, please.
Yes, of course the presentation is open, and there will be no problem to send it to the people who are interested in.
Mm-hmm. Thank you. Now, there was another question to your presentation, actually, where it is asked if slide 18 is NMR based in your presentation.
To look. The answer is no. This was a vitamin B12, and this was a classical clinical chemistry assay. This was an example to show that in general clinical chemistry, when we change our platform, that we observe in many cases relevant shifts between platform A and platform B. And this is one of the real advantages of the NMR spectroscopy, that in this view we do not have any changes in accuracy. Okay? Hello?
Dr. Sproul? Oh, it appears that Dr. Sproul has lost his connection. We do apologize. There are quite a few questions that are still in our queue, and I see more coming in. Those questions and those submitted during the on-demand period will be addressed by the speaker via the contact information that you provided at the time of the registration. Additionally, a short exit poll will pop up on your screen. Your feedback is important to us. Thank you so much for participating. We would like to thank Professor Matthias Nauck for his time today and his important research. We would also like to thank LabRoots, Mr. Manfred Sprawl, and our sponsor, Bruker, for underwriting today's educational webcast. This webcast can be viewed on demand through May of 2019. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.